Good afternoon, good evening, good morning. Actually, I'm Tadashi Okoshi from Keio University, Japan. I'm connecting this from Tokyo. So yeah, it's at night in Tokyo, but mainly for people in Europe, good afternoon. And I'm happy to invite our keynote speaker, Professor Joyce Wesserink, with a fascinating keynote title, Cortisol as an inspiration and ground truth for the development of a skin conductance-based stress indicator. So, hello, Joyce.
Hello, everyone. Hello, Tadashi.
So, yeah, let me introduce you with your bio. So, Professor Joyce Wesserink was originally trained as a physicist, and afterwards she expanded her horizon towards human technology. And she's affiliated with Philips Research, where her research focusing on psychological topics in a technological context, such as visual perception, image quality, human factors, user interfaces, and more recently, psychophysiology in the context of emotions, well-being, and affective computing. So she currently holds a chair on well-being and psychophysiology and human technology interaction at Eindhoven University of Technology. Sorry, for me, it may be difficult to pronounce. Eindhoven.
Absolutely correct.
Right. Thank you very much. And written output, her work can be found in some 50 articles and books and international journals, and some 50 patents and patent applications. So yeah, I'm happy to invite Joyce here in the Emotional Aware workshop. And please start. Thank you.
Well, thank you for the very nice introduction. I think that the first thing that I need to do is then share my screen with all of you. Let's see whether that will work. This maybe. Okay. Does everybody see the screen at the moment? Yes? Okay.
Yes.
So this is what I'll be talking about today. I'll be talking about a stress indicator that is used in wearables. And I'll be talking about how we developed it and what the important role of cortisol was in that development. And this is work that we did at Philips, and you see a whole list of co-authors for this presentation. Those are my colleagues at Philips. We did that together, like at Philips, we do most things in bigger teams. Right. So let me start with the wearables and the stress. Wearables are everywhere, right? There is a great lot of lifestyle related parameters that you can monitor. You can monitor your weight, your fitness level, and most of you will already be doing that. And very often that is then measured with a combination of PPG, photoplethysmography, and accelerometry. And within that context, also stress is gaining more and more importance as an important parameter. And if you think of standard psychophysiology, then stress is connected to the measurements of heart rate and heart rate variability, and also to the measurement of skin conductance. But on the other hand, it is also clear that monitoring stress is not that simple. And there are a number of reasons for that. And one is that stress is often seen as a subjective experience. So what you would like to do with your monitoring is that you would report something that is in line with these subjective experiences. But usually these correlations are not that high, and they are off the mark too often. You normally want that they'd be, let's say, correct 90% of the time, so that the remaining 10% you still have trust that that is correct too, but it's just your personal perception that is off. But if it's off much more often, if it's only correct 50% of the time, you don't trust anything, do you? So that is why it's difficult to monitor stress. And there is another thing that was bothering us with stress, with subjective stress, and that was the idea, okay, and then if you have this subjective stress as an estimate, how can you easily translate that into something that is relevant, that tells you, okay, for this stress level, you need to do this, and for that stress level, you need to do that because of the impact of the stress. So that is also a difficult step. And those two elements, you will see that we have found cortisol as a bit of a solution. So our research question was, can we find a good measure for stress that can be used in wearables? And of course, I already give a bit of a spoiler that the solution that we have there is cortisol. We take that as an inspiration, actually, rather than a ground truth, because we look at cortisol. It's known as the stress hormone. It is part of the HPA axis, which is the axis in the body with all the hormones that reacts to stress. And cortisol specifically helps to deal the body with stressors. And it's known that if you have high levels of cortisol, you get slower cognitive functioning. So here is a bit of the impact of cortisol on your actual functioning. If you want to measure cortisol, that is mostly done in saliva, the fluid in your mouth. It can also be found in blood, but that's very intrusive in order to get that. And it can also be found in your hair, but then of course you only look at the long-term changes. Cortisol is known as one of the most accurate measures of stress. So that's a good thing. On the other hand, the biosignals that you pick up on in wearables, they do not measure the hormonal activities. They measure the activities of the ANS, the autonomic nervous system. And as you know, the autonomic nervous system has two branches, the parasympathetic and the sympathetic branch. I presume that the sympathetic branch is known as the fight or flight system, which mobilizes resources whenever there's something urgent that we need to deal with, for instance, a lion that is standing in front of us. And the parasympathetic system is actually the rest or digest system. It is the system wait or to relax in order to recuperate from the stressful events that were there before. And you can see that actually all of the organs in our body are under control of both the sympathetic and the parasympathetic system. They are in fact the gas pedal and the brake of our body. And just as in a car, it is possible to press both pedals at the same time, although the results are not so good. And if you see in this is under the innervation of only one of those two systems, namely the skin. You can see the sweat glands and also the hairs in the skin, in the circle, that are only under sympathetic control, only under control of the fight or flight system. And for that reason, it is good to measure the activity of the skin innervation, specifically because sweat glands are
sorry, Joyce, may I please interrupt you? For us, we have some technical problems. Maybe you can switch your camera off just for a while, because for us the speaking is broken.
Okay.
Maybe that will help, or is it fine for the others?
I'm fine if you switch my camera off. Can you do that for me, Judith?
Yes, I will do. I will try that. Is it now off?
I don't know. I still see myself, but you.
Okay. How is it for the others? Maybe it's a problem from University of Kassel.
There was also this problem for me, and now her video is gone.
Okay.
Okay. Okay.
All right, but so, maybe this will help. Thank you.
Judith, please switch my camera on and off as you please. Right? Whatever you think is needed. I will continue. I will continue then. But the remark that I was making, that we want to measure this activity of the sympathetic nervous system, and that sweat gland activity is a good candidate for that because it's innervated by only the sympathetic nervous system. And the way that it's measured is by picking up on the fact that the autonomic nervous system, if it's active, it triggers the sweat gland in to produce sweat in the ducts. And that raises the water content of the skin. And as you know, water is a conductor, so that raises the conductive capacity of the skin. So skin conductance is a measure that tells you something about the autonomic nervous system. And now we have these two components. We have skin conductance that we can measure, and we have cortisol that we'd like to take as our inspiration. And the thing is that we have to link them together, because of course, since they both have to do something with stress, we expect them to be correlated in some way. And this is and this is the way that we have modeled the relation between skin conductance and cortisol. So the first thing we realize is that they are both the results of a same emotional stressor. So if something happens that is really stressing for you, for instance, at the beginning of this graph, at the very left end of it, then our body will have two reactions. One, there is the reaction of the skin, and the skin conductance will rise, and that will happen within a few seconds. Within 10 seconds, you will have this skin conductance peak. But there is also a second reaction, that is the hormonal reaction that will produce cortisol. And that will be much slower. That on average is 30 minutes later, right? It's known as the cortisol response curve. So what you could actually say is that each skin conductance peak that you see actually predicts a cortisol peak that is 30 minutes later, or actually it's 30 minutes minus 8 seconds later, but okay, it's 30 minutes later, right? And so this is something that we took as a beginning. And then as good engineers, we made the next step. We said, well, let's assume that it's linear. Let's assume that if the skin conductance peak is higher, this means that the cortisol peak will be higher as well, because there must have been more stress, right? So we are assuming that this is linear, or at least we are approaching it with the idea that it's linear. So that's the first step. And then the second step is determining what will be done if there are more skin conductance peaks. So here in the graph, what you see is that
Did we lose her?
Yes, I think so.
Yeah, let's wait a while.
Yeah.
It may take some more time. So everybody, it seems that the internet connection from our keynote speaker has been lost. I hope it's temporary.
I'm back again. I think we lost it, but I'm back again.
Oh, hi, welcome back.
Yes,
It's nice to have you again.
yes. I'm sorry, I don't know what happened. Shall I just try and continue?
Sure, please, thank you.
And then I will share my screen again. Oh, can you enable me for screen sharing?
Yes. Now it should be possible.
Okay.
So you were talking about the peak of the cortisol.
Yes.
Was,
yes, I was at this
linear.
slide, right? I think I got stuck at this slide.
Right now.
That's true.
Yes. And did you all already get the idea that each skin conductance brings about a cortisol peak? Yes, right?
Yes.
And then the next step, the step that I was explaining here, is that if you have a trace of that runs from the early evening till the late evening, in which there are a number of skin conductance peaks, 2 big ones on the left side and 6 lower ones on the right-hand side, that we assume that each of those skin conductance peaks will bring about its own cortisol response curve, right? And you see those cortisol response curves on top of the graph. And because these cortisol response curves are so extended in shape, they will partially overlap. And what we then do with all these overlapping cortisol response curves is that we just add them all up, right? We add all the overlapping response curves up to estimate the amount of cortisol that is triggered by this stress thing that also triggers the skin conductance bonds. And this measure, we call it the estimate of stress-induced cortisol, right? It's not all cortisol, but only the cortisol that is induced by stress, as we picked it up from the skin conductance-based signal. And what you can see in the graph here is in black, the skin conductance signal, yet another signal from 8 in the morning till 4 in the afternoon. And the ESIC value, the estimate of stress-induced cortisol in green that we calculated from it. And yet what you can see is that there are a number of skin conductance peaks in black, and that usually sometime later, there is a rise in the ESIC value. And that adds up for a number of the peaks. And then if there is a relatively relaxed period, for instance, between 11 and 12 o'clock, then you see the cortisol drop as well and keep dropping later. But then when around 12 o'clock, there is again a skin conductance peak, you see the cortisol rise 30 minutes later again. So that is the model that we have made of the relation between skin conductance and cortisol. Let me talk to you a bit about the mathematical aspects of that model. Well, first, a recap of the steps. We take skin conductance as input. We determine the skin conductance peaks in order to determine the moments of stress. We determine the skin conductance peak heights in order to determine the intensity of the stress. And then we compute the expected cortisol response for each of those peaks and add everything up. And that mathematically amounts to what is called a convolution of the skin conductance peaks with the cortisol response curve that is known from literature. And this processing more or less resembles adding a 30-minute delay because the cortisol response curve is much lower, in addition to applying a low-pass filter because the cortisol response curve is more or less bell-shaped and with a wide range. So what I also want to point out is that this model needs a history of data, because as you've seen, this cortisol response curve, it takes 30 minutes to reach the top, and then it decays very slowly. So all in all, the cortisol response curve lasts 90 or 100 minutes. And we have implemented such a 100-minute tail to the cortisol response curve that we take as a convolution kernel. But that means that we also can assume that there is still a tiny bit of impact at the moment from a skin conductance peak that was present 100 minutes ago, because that skin conductance peak, if it was present 100 minutes ago, it had its peak at 70 minutes ago, and it still extends until now, right? So we need a history of data to actually model this. Well, that is complicated, but there is also a very positive aspect to the fact that it takes data from a time period, and that is that this model can predict the future. Because if the skin conductance peak is there now, we know, we can predict that in 30 minutes from now, there will be a cortisol peak. And that is something that is really interesting for applications. Right. So now I have explained to you the model. It is, of course, it's a nice model, but it's even nicer if you can experimentally verify that it's correct. And this is what we set out to do. So our research question became, do skin conductance-based estimations of stress-induced cortisol indeed correlate with cortisol concentrations and their fluctuations in the body? And as you see, this is the moment where our cortisol that we had as an inspiration now changes into something that becomes a ground truth, because this is what we want to test our ESIC predictions against. Do they indeed correlate with cortisol concentrations in the body? And the way we did that is that we set up a 4-hour experiment, and it involved a wide range of saliva cortisol concentrations that we measured. And the way that we measure them is with salivettes. Those are swabs of cotton that you take into your mouth for, let's say, a minute or so. They soak themselves with your saliva, and you collect them and you send them off to an analysis lab that will then determine the concentration of cortisol that was in your saliva at that moment of time. And what we also do is, at the same time, we measure the skin conductance. We used our DTI-5 device for that. It is CE marked, although it's not on the market. And that allows us to measure skin conductance during the experiment, and actually already some time before, because we wanted to take that 1 hour, that 100-minute tail into account. And then what we asked the participants to do was 3 types of tests. We asked them to do a psychomotor vigilance task, which is a very boring task. We asked them to do an NBAC task, which is actually a cognitive performance task. And we asked them to do the trio social stress test, which is a stress test inducing social stress. So this is the experimental procedure that we did. We had psychomotor vigilance task, the boring task, in a dark room for 60 minutes. And it's really boring because you're asked to look at the screen all that time and press a button whenever you see a slight gray dot somewhere. Then you have to react, and your reaction time and your accuracy are measured. And during that task, at certain moments, we took 3 saliva samples. Then there was a pause in which they could drink water and tea. And then we started with the cognitive task. It's an MBAC task. Then you get a number of letters that are presented to you in sequence. And for each letter, you have to determine whether that letter is the same as the letter that is n positions back. Well, if it's a 1-back task, that's easy. Then it's just, is this letter the same as the previous one? But that task we didn't do. We did a 2-back task. So is this letter the same as the letter before the previous one? And we did a 3-back task. Is this letter the same as the letter 2 positions advanced? And during that MBAC task, we took 2 saliva samples. Then we asked the subjects to score how they felt with the positive and negative effect scale. And then we did the trio social stress test. That is really a stressing test because people are informed that they are about to give a presentation for a job application. We gave them information about a potential job, and we said that they would have 5 minutes to prepare a presentation that they should give. And then they got 5 minutes to actually present in front of a panel that was instructed not to react positively or negatively. And everybody knows that this is not a real job interview and nothing depends on it, but people get stressed. Nevertheless, it functions. Then we did again a scoring of positive and negative effect, and we did again an MBAC task, and then we did an exit interview and debriefing. And for all these moments, we took saliva samples just to monitor that cortisol level. So now we come to the results. And the first thing, of course, to look at is, did we manage to induce enough variation in the in-body cortisol with all those tasks? And yes, we did, because this is the 9 moments, the 9 saliva samples that we took. And you can see that there are significant differences in the cortisol concentrations measured in minimal nanomole per liter. You can see that there is, for instance, a significant difference between the cortisol concentration at the first and at the 4th measuring moment. And that difference is the difference due to this PVT task, because apparently it was boring and it kept being boring. And by the time that they were at the break, at the 4th PVT task, the cortisol level had dropped considerably. The major increase, of course, you see at measurement moment 8, and that is due to the trias social stress test. You would say, oh, then I'd expect it to rise at measurement point 7. But remember, there is a 30-minute delay in the cortisol reaction, right? So measurement point 8 was actually constructed to be roughly 20 to 30 minutes after the trias social stress test. And yes, we see the increase there that is significant and that we expected. The only thing that was surprising to us was that this increase was not there for everybody. So usually when you go to literature, you always see these average results and you see, as we see, an average increase. But when we looked at the individuals, there were some people who did show that increase and other people who did not. And we split them up in 2 groups. 22 participants did what we expected. They showed a cortisol increase after the TSST, but 6 did not. And if you look at how their curves differ, this is what you get. For the black squares, you can see the increase that we've seen before. And for the open circles, that is the low cortisol responder group, you don't see it. They really are unexcited by this task. By the way, one of these persons actually was somebody, a coach, who prepared others for job interviews. So for this person, you do not expect it. Other people performed really well and seemed to enjoy it. So we can understand that there are 2 groups. And we thought that for the rest of our results, we might make sense to split up our results for these 2 groups. So that is what you will see in the next coming slides, because now we will look at what happens, for instance, with the performance during the psychomotor visual task. You can see the reaction time as a function of time. And you see that the reaction time increases. And that is because you get bored and you get a bit drowsy, so your reaction slows down. This is known from literature, and you see that it takes place for both groups, the high responders and the low responders. And of course, it takes place for both groups because this PVT task, it was before the trias social stress test. So there is no difference yet between the 2 groups because the thing that makes the difference is still to come. So here we don't see a difference, and that's exactly what we expect. Then have a look at how people felt, the self-reports. In the green columns, you see their scores for negative effect before the trias social stress test and after the social stress test. And that difference is significant. And that is what you expect because, as I said, the trias social stress test is not a nice stress. So of course your negative effect goes up. Your positive effect did not change very much. And what we also found was that there was no difference between the high responders and the low responders. So even though their bodies changed in a different ways, their self-reports did not changed that much. There was no significant difference between them. And this brings back to what I said in the beginning, that sometimes these self-reports are not a real reflection of what is happening in your body. Right. So let's look at some more results. Let's look at the results of our cognitive test, or MBAP task, that was done before the TSST, as you remember, as well as after the TSST. And here you can see that after the TSST, the mean reaction time in that MBAC task, it decreased. That means that people learn, right? So at first, when they did it before the TSST, they had a certain reaction time that they needed, but they got better at it. So after the TSST, their average reaction time was lower. That is understood. But what you also see is that the two groups do not have the same decline between before and after the TSST. The high cortisol responders, they have some improvement in their reaction time in the sense that it gets less, but the low cortisol responders have a much bigger improvement in their reaction time. It gets much more or less, and this interaction is significant. So here we can see that the high responders and the low responders, they react differently in this second session, and the high responders show less improvement than the low responders. So here we have proof that whatever has happened has impacted their functioning, even though their self-reports didn't show a difference. Right. So far, I've not been talking about skin conductance yet, but that is what I'll start doing now. First, I'll bring back to your memory what we did. And what you see in this graph in black is the skin conductance trace again, where you can see that there are some severe peaks. And the last severe peak is the 3-year social stress test. And then in red, you see the estimates of stress-induced cortisol, the ESIC calculations that we derived from that. And you could see that each cluster of skin conductance peaks is followed sometime later by an increase in our ESIC value. Then you also see these vertical green lines. And those are the moments at which we took a saliva sample. So although we can continuously calculate our estimation of stress-induced cortisol, we can compare it to what is actually happening in the body only at those moments where we also took a saliva sample. And that is at the moments at the green lines. And that is also the correlation that we'll make in the next slide. So here you see the comparison between our ESIC values that were derived from our cortisol, skin conductance measurements and the actual saliva cortisol. The cortisol is in orange and the ESIC values are in blue. And you see on the left side what happens for the high responders, and on the right-hand side what happens for the low responders. And for the high responders, as you can see in cortisol in the orange line, after the TSST, the main thing that happens is this a big increase in cortisol level. And for the rest, you see the decline somewhere between sample numbers 3 and 4 because of the impact of the drowsy PVT test. And you can also see that more or less our ESIC predictions follow this really nicely. The blue line more or less coincides with the orange line, not completely, but it's a nice correlation. It's 0.74 and it's significant statistically. On the right-hand side, we have the low responders. Those people in their orange cortisol line, they do not show the TSST peak, of course not. That's what we selected them for. And you can see that also in the ESIC predictions that we made for them, that peak is absent. And also here we find a nice correlation, and it's just not significant, but almost. So what we, for both groups, we find that our ESIC predictions follow more or less the measured cortisol, and that's reflected in substantial correlations. Well, that's nice, but that are group results. And if you're thinking of a device that is used by an individual, this relation also needs to hold for an individual. And this is, for instance, a plot for one individual And you see in total, there are 9 moments at which we had a sample. And what you see is how these, for these sample moments, the measured cortisol is related to our ESIC predictions. Our ESIC predictions are on the horizontal axis and the measured cortisol is on the vertical axis. And this is for one participant. And you can see a very nice correlation. It's one individual participant. Correlation is 0.76 and it's significant. That's nice. This is not the best participant. It's also not the worst participant. And actually, this is the graph of all participants that we had. So you see some participants actually had a very good correlation that was nearing a correlation of 1. And well, I presented here them in order. There are also correlations that are really low and also negative. Actually, from the 28 individual correlations that we could calculate, 10 were positive and significantly positive. 12 were also positive. That is above the line, although they were not significant. And there were a number of them, also 6, that were negative. And thank God they were not significant. And you can see that the low responders, they were not at either end of this curve. Some low responders had nevertheless very good correlations, and some low responders had very bad correlations. They were nicely distributed. So apparently, whether you have this correlation or not does not depend on whether you're a high or a low responder, which is good, which means that in practice, our device can work with both types of people. Well, of course, we would have liked that everybody had a significant positive correlation. In practice, you do not always find that. So our first guess was we would like to get an average impression. What was the average correlation of all these individuals? Well, if you calculate that average correlation, you have to do a Fisher correction. If you do that, you find an average correlation of 0.48, which is very nice, actually, considering that you're looking at physiological data. And then we also did the test to see whether that is a significant correlation. And yes, it tests significantly different from 0. So on average, we'd say that there is a relationship between our skin conductance-based ESIC values and the saliva control that is significantly different from 0, and that on average has a value of 0.48. Right. So that is what we figured out. And of course, well, you always start a discussion with asking some questions to yourself. Of course, the main thing is the limitations. This is just the first test only. It is done under laboratory conditions. And as you must have noticed, our ESIC conditions, our ESIC estimations are in arbitrary units. That means that we are only able to predict relative cortisol changes. And for that reason, we also took a correlation as a measure. We are not capable of predicting absolute cortisol levels. But these limitations, of course, then also imply further lines for future research. It would be interesting to get a more detailed understanding of the link between these two physiological processes involved. It would, of course, be really interesting to go to live circumstances to check that this relation remains applicable. And it is interesting to check the applicability and the personalizability of individual use as a stress indicator for wearables. See whether we can make it better for those people who currently still have a negative correlation. So what is it that I'd like you to take home from this presentation? Well, first is what I'd like you to take home is the stress more quickly. It is possible to predict the stress-induced cortisol levels from skin conductance ahead of time. If you see skin conductance now, you know what's going to happen with stress-induced cortisol later. And this model is supported by initial experimental results because it showed a significant correlation between e-cig and saliva cortisol. The second thing that I want you to remember is that since the increased cortisol levels are associated with reduced cognitive functioning, we know that from literature, and we saw it in this experiment as well. The e-cig prediction is relevant for applications that try to coach people for a good mental balance, because we can accumulated quite some e-cig value now. So this might be a sign that it's better for you to start to relax or break or make a pause now, because otherwise you might not stay in the optimal zone. Taking a step back, what we have done is taking cortisol both as an inspiration for a model, as a ground truth for a verification in the development of a stress indicator, and it pays off because we get less variability due to the self-reports, and we get cortisol, which has direct implications for cognitive functioning. Well, that is what I wanted to present to you. Maybe there are some questions.
Thank you very much, Joyce. So,
Pleasure.
I enjoyed your talk very much, and I wrote down a bunch of questions for you, but from the audience firstly. So, any questions? Or raise your hand. Oh, David, Klaus.
Yes, thank you. Great talk. I was just wondering, so skin conductance, Joyce, I believe is also influenced by something which has nothing directly to do with stress level, like if you were just moving up some stairs, or if somehow the room temperature changes, becomes colder or warmer. This also has an influence on skin conductance, right? So how important do you think such effects are? And cortisol level, is there also something which is not related to stress, which changes this level, or is this really the gold standard, which is 100% stress only?
Well, this is a very good question, and in two sentences, you summarize a lot of the problems that we have to deal with. One of the problems that you mentioned is that during movements, your skin conductance trace might show artifacts. This is known if you have a wristband, it has to make a contact with the skin, and if you move, this contact can change slightly, and that can cause a change in the skin conductance level measured. And this obviously is an artifact, it's not something that you want. And we have been able to overcome this by modeling our skin conductance peaks and only selecting the ones of which we are certain that they are normal skin conductance peaks. So that is a trick in which you can throw out artifacts like that. Mm-hmm. A second thing that you remark is that skin conductance is known to vary also under the influence of other factors. You mentioned room temperature, that's a known factor. There's also another factor, and that is if you are sweating, for instance, due to physical activity that you're doing or have just been doing. And this influence is known to very much impact the skin conductance level. But if you remember, we looked at the skin conductance peaks, right? And those skin conductance peaks can be on top of a low average level, but they can also be on top of a high average level. So what we have found is that if you look at the number of peaks and the density of the peaks and maybe the accumulated height of the peaks, you forget about what the average skin conductance level is. So you have less of an error that has to do with these factors. And then you had a third question, but I'm trying to...
Cortisol, and whether it only is related to stress or also to some other factors.
Yes. our interest is in stress. So this is what we wanted. And Zelje, of course, the person who coined the term stress, he defined stress as any reaction of the body. But for us, it turned out to be relevant to limit itself to the stress that is induced by the changes that are induced by emotional stress. So for instance, if you are walking the stairs, but not emotionally stressed by it to some extent, we don't find that relation with skin conductance that much.
Okay, thank you very much. Oh, I think has she dropped out again?
It seems so.
Yes. Yeah.
Yeah, she'll be back, I think.
Okay. Is it okay for you if we stop the recording now and restart it again? Because this will take a few minutes, just like 1 or 2 minutes. Yeah.
I think so, yes.
Okay, thank you.
And you still have multiple hands, so.
So she must come back.
So, okay, we still have multiple hands. Yeah, let's, so Przemek, sorry, I cannot pronounce your name very much.
Yeah, my name is Przemek.
Yeah, it's your name.
From Poland.
Przemek.
Yes.
Sorry, that.
No, it's okay, don't worry. It's Slavic name that exists only in Polish, unfortunately. Sorry also for not having the camera, but my hardware is broken. I don't know why today. But anyway, coming back to the point, thank you very much for the very interesting talk at first. And I really liked your individualized research, so that you have tried to look at the single subjects. And my question is, have you tried to identify the factors that makes these people different? I mean, in particular, the biology, the production of cortisol, which could be slightly different, and the reaction or organized slightly different for each of the person. And another one is the general attitude towards the task and to the stimuli that invoke the stress. It is like you mentioned about this coach that was used to prepare people that maybe it was not so stressful for the person. But I also mean about the personal traits. So some people are maybe not so stressful in general, so experience their life slightly different than the others. So what are these two factors, at least? Of course, they are related to each other, but in general, we can also think about each of them. Yeah, thank you.
Yes. So yes, I understand your question. Let me answer by first saying that because we were interested in making a stress indicator that was for use in daily life for a wide group of consumers, we wanted to work the thing for all, right? So our inclusion was very wide. We needed to have people that occasionally experience stress and that were adults, and that was about our inclusion criteria. And so that and we want to that was the main research question, that it works for all. Of course, now you see these results. It is interesting to see whether there might be specific characteristics for which okay, maybe it works more in this case than in that case, and that would be interesting to look into. And we have tried to do that in a second follow-up experiment, which we are currently analyzing, and it looks like we can find some indicators there indeed that tell us more about what is going on there on a personal basis. But indeed, involves measuring a very wide variety of personal characteristics that you think might be able to do the job in predicting these differences.
If I can one remark to that, I think that in general, affective computing is so specific regarding the individual. So I think that in general, we should think about the solutions which are a bit more personalized than only generals.
Yes, indeed. I completely agree with you.
Like just different. So
Yes.
that's the point.
Yes.
Yeah?
And this is also our path to optimizing, to improving the results.
Exactly. But on the other hand, we need to collect some data from the long-term studies. It's not just for the one shot.
No, that's another limitation that at some point we need to go to real life, right?
Yeah, exactly. Yeah, thank you.
I agree.
Thank you. So next question is from Yoshito. Are you there?
Hello. Okay, so my question is very simple. The delay from the peak of skin conductance to the peak of cortisol is quite large. So will you explain why the delay is so large?
Yes. Well, no, I cannot. That is because I am not an expert on the hormonal processes in the body. So my guess is that if there would be an expert on the hormonal processes in the body and the diffusion and the production of hormones, he might be able to actually model why it takes 30 minutes for the body to come up with a peak. I only know that this is known and measured in literature. I also know that cortisol, although it's known as the stress hormone and is known as a measure for stress, it is actually the hormone that combats stress. So that makes it sense that it's not high right at the moment, but that it is high at a later stage if it has been prolonged for a while, because at first you need the stress and your body to react to it, and then only later you have to calm down.
Okay.
But actually explaining why the body takes 30 minutes to build up, I cannot do that. This is a question that is better asked an expert in cortisol processes.
Thank you.
And sorry to that, have you observed any differences between people in this 30 minutes? So that somebody reacts faster or slower?
Yes, we have scanned all literature to see whether there are any differences in the time it takes between individuals, in the time it takes to increase and decrease the cortisol response. We found only reports of average cortisol values, averaged over participants, not of individual participants. So in the experiment that I was just referring to, that we are currently finalizing the analysis of, we looked into whether there are indeed significant differences between people in the rise and decline times of their cortisol response scores, and we found them. It's just that they are not reported in literature yet because nobody was interested in them up till now. But then we did our own experiment and we found it.
Yeah, great, thank you.
Thank you very much. Very interesting topic. And okay, so we have another, can I say Yasha from ETH.
Hello. Thank you. That was a really, really interesting talk. Our lab has also used a lot of skin conductance, and we noticed that especially with mobile sensors, there is a lot of disparity between the quality of the skin conductance results compared to medical grade ones. So I'm not sure if I missed it, but how good does your arm wrist sensor work with this regard? And would the results be different if you use medical grade equipment? And can you maybe go a little bit into the details there? That would be great. Thank you.
So first, would the results be different if we make medical grade equipment? Well, traditionally, skin conductance is measured at the palms of your hands, right? Either in these positions or in these positions, right? That is where you traditionally put your electrodes when you do a laboratory skin conductance measurement. And those positions are really awkward for daily life, so we put them on the wrist, and that's a different position. The density of sweat glands is different on those positions. And so if you do the measurements, you will see that the pattern of peaks is different also. There is a nice publication that everybody in literature cites by a colleague of mine, Marieke van Doorn, who actually compared a whole lot of places on the body. So there are differences that we know. And now, although we say skin conductance is a measure of the sympathetic nervous system, we see that if we pick up on it in the sweat gland activity, there are differences between what is measured in the palms of your hand and what is measured on the wrist and what is measured on the other wrist even, right? So there are differences there, and knowing that these differences exist, you can go two ways. You can try to explain why these differences are there. That is typically the academic route. Or you can say, well, we are looking at what at least is in common, and we'll try to use it for practical application. And that is the industrial route, of course, and that's the route that I've been presenting to you now. Then there is also another part to your remark, and that is that especially in these wrist-based measurements, there are a lot of artifacts. So not even the true measurement would be different, but it's also that you get extra artifacts at the wrist. That is a nuisance, of course. But on the other hand, if you want to use it in real life, this is what you need to deal with. So what my colleagues have been doing, and you saw the many names that contributed to this publication, is that we have implemented processing that tries to assess the quality of what the skin conductance signal is for making this estimation. So basically, we do not only make the ESIG estimation, we also make an estimation of how certain we are of this value. And sometimes there is so much artifacts that we say, well, we can make an estimation, but we're not at all certain about it. And you can set the threshold for the quality that you want to a certain level. There is also, but that was also already an answer that I gave earlier, there's also that we try to improve the processing overall in order to, of course, recover as much as possible. And one of the tricks is to try and identify each of the individual pulses so that you can throw away those variations that are, for instance, much steeper than any skin conductance pills could be. So they must be an artifact. If you throw them out and you know that you only are left with the true skin conductance peaks, then that is a step forward.
Thank you.
Okay, you're welcome.
Thank you, Joyce. So, Judith, are you going to ask a question?
Yes. Thank you very much for the presentation. I've got a question about the skin conductance as well. So you said that there were people for whom the cortisol level was really low, even during the stress test. Yes. How was it about the skin conductance? So did they react with the skin conductance as well with a lower level or not?
No. So that is exactly why also this group of people had a good correlation, because no, they didn't react with cortisol. There was no cortisol increase in the body, but they didn't react with skin conductance either. So that was really in line, right? So we tried to apply a stressor. The stressor didn't work. But even in situations that the stressor doesn't work, you still would expect that for that particular person, the correlation between the two should stand up. And it did. Yes.
And for other works, like I know one work from Chelsea where she measured the stress level of car drivers, and they had like some some participants reacted without any external stress stimulus, but it was because they made a bad experience at this corner. So would you assume that the cortisol level will also increase at this part of the street, even if there is no stressor?
Yes. So what we assume is that whenever we have an emotional stressor, there are two things that react: your skin conductance and your cortisol. And it doesn't matter that much whether that stressor is an external stressor or is something that you think of, that you suddenly think back of this very dreadful situation that you're in, or this presentation that you have to give, or whatever is coming up, right? Whether it's imagined stress or imagined stressor or real stressor, doesn't really matter. We haven't been able to research that in all varieties, but one thing, for instance, what we investigated is stress in a virtual reality situation. Maybe some of you know this virtual reality setup where you're at the top of a skyscraper, and then from that skyscraper protrudes a wooden board that extends, let's say, 2 or 3 meters into the open sky, and you can imagine that you walk on it. In reality, of course, you just walk on the floor, right? To some extent, it's imagined stress, but it works for some. And then their cortisol as well as the skin conductance go up.
Okay, thank you.
Thank you very much. I think we had a lot of questions and answers, and amazingly, enjoyable talk and keynote. And thank you very much, Joyce, again. So please push the reaction button to so give some appreciation. So thank you very much, Joyce. It was very happy to have you.
It was a pleasure to be here.
Hello, everyone. Welcome to the third day of ICPC 2021. It is my great pleasure to introduce our keynote speaker, Joyce Westerink. As the first keynote, also in this case, we are a bit outside our comfort zone, meaning that Joyce is not a part of the program comprehension community, but will allow us to understand some complementary additional properties connected to program comprehension. Joyce is employed in Philips in the Netherlands, and also at the Technological University of Eindhoven in the Netherlands. Her key areas of psychology, physiology, user interfaces, human-computer interaction, and stress. And today, she will be talking of an algorithm to estimate stress-induced cortisol variations from skin conductance measurements. Thank you very much, Joyce, for being here, and the stage is yours.
Well, thank you. Thank you, Fabio, and thank you, Alexander and ICPC for the invitation. It is a pleasure for me to tell you about the work that I've been doing, and indeed, it's not in program comprehension. What we try to make is an algorithm that estimates variation in the cortisol that is in your body, but it bases those estimations on measurements of the skin conductance that is measured with a wearable. And this is work that we have been doing with a team at Philips Research, and you can see the extent of our team, which includes engineers, psychologists, hardware, software engineers, so quite a wide bunch of people. So let me start with the beginning. And to start with the beginning is the fact that wearables at the moment are omnipresent. They measure a very much lifestyle parameters. And I think that most of you are currently wearing such a wearable that measures heart rate and gives all sorts of parameters about maybe your fitness and your sleep and your activity. And very often it's measured by means of a combination of PPG, photoplethysmography, and accelerometry. That's usually in there. And what we find is that stress then is also gaining attention. And of course, that is also because it is an important lifestyle parameter. Stress is important in our daily lives as well. And if you think of which physiological parameters are then relevant for indications of stress, there are two parameters that stand out in literature. One is the variability in our heart rates, and the other one is the skin conductance. And that is just physically the conductance of your skin as measured between two electrodes. And it depends on the water content in the skin. And with it, it depends on the content of the sweat in the sweat channels of your skin. So skin conductance basically is a measure of how much sweat is in your skin, and the amount of sweat is triggered by your nervous system, right? So it would mean that you could take either of these measures and try to monitor stress. But that is not so simple, because stress is often seen as a subjective experience. It's something psychological, and psychologists tend to emphasize that this is something that people experience and that cannot be measured in any objective way. It can be measured reliably, but in a subjective way. Nevertheless, what you see is that those subjective measures, which usually include self-reports, you ask people to say how stressed they feel, usually you find that those self-reports of stress do not correlate that well with those physiological measures of skin conductance and heart rate variability. So there is something to be gained there. And also, because the self-reports are presentations that do not have a natural boundary, it is difficult to interpret what is the impact of a high stress level. So why is that bad, or what is that bad? And so in this area of uncertainty, we continued the search for a good measure for stress that can be used in wearables. So that was our research question. And the approach that we took was that we started to look at cortisol as a source of inspiration. So you know that cortisol is the stress hormone, and it's part of the so-called HPA stress axis. It helps our body to deal with stressors, and we know that high levels of cortisol lead to slower cognitive functioning. So we have some indication of the impact of cortisol on the cognitive functioning of the body. Cortisol can be measured in many ways. It can be measured in hairs, and it can be measured in blood, but those are really difficult ways to measure it. And a relatively easy way to measure it is in saliva. Generally, cortisol is considered one of the most accurate measures of stress. It's considered basically the gold standard in the endocrinological world. But that's one way of looking at it, the hormone. There is also the way of looking at it from the autonomous nervous system. And you see a picture on the right-hand side. So the biosignals like heart rate and heart rate variability, they are usually measured in terms of the autonomous nervous system. And in this enlarged picture, you see that this autonomous nervous system has two branches. On the left one is depicted what is called the sympathetic branch, and we know it better as the fight or flight system. When it's active, it provides resources to our body to cope with situations that need our immediate reaction now. For instance, when we see a lion, we need to be able to run. And the autonomous nervous system, specifically the sympathetic branch, will trigger all the organs in such a way that this is facilitated. On the right-hand side, you see another set of innervations. Those are the nerves of the parasympathetic system. And that system is known as the rest or digest system. And it becomes active in terms to foster future development and growth. So rest is important there, but also the recuperation of muscles and things like that, and the digestion of your food. What you see is that all the organs are innervated by both the sympathetic and the parasympathetic system, basically meaning that both systems are triggering what these organs do in a sort of combination. And there is one exception to it, and that's in the circle that's over here, and that is the skin. And especially here, the sweat glands that I already mentioned, those are for some reason only innervated by the sympathetic stress-based system. So this is one of the reasons why we look at sweat gland activity to measure skin conductance to give us an idea of the activity of the autonomous nervous system. So what we have now then is skin conductance on the one hand and cortisol on the other hand, and we want to link them. And the idea is that we do that by considering the fact that both cortisol and skin conductance are both direct results of a singular stressful event. So in some way or another, we expect them to be correlated. And here is a picture of what happens when there is a stressful event. One thing that happens is that if here is the stressful event, there is a skin conductance response almost immediately. It is within a few seconds. There is also a cortisol response, but it's much later, and it peaks roughly 30 minutes later. This curve is called the cortisol response curve, and it has been measured in literature throughout, for instance, by Kirschbaum and colleagues. So the engineering approach that we took was that we said, well, okay, apparently one skin conductance peak actually predicts a cortisol peak roughly 30 minutes later. And then as really good engineers, we said, well, okay, then we just assume that it's linear. So that would mean that a higher skin conductance peak would also predict a higher cortisol peak 30 minutes later. Right. That was step one. Then step two was that we said, well, what will happen if we have a series of skin conductance peaks? As you can see in the graph down here, there is a series of peaks. And what we assume is that each of these peaks triggers its own cortisol response curve. And what we also assume is that the higher peaks trigger higher cortisol response curves and the lower peaks trigger lower cortisol response curves. And what you can see is that these individual cortisol response curves, they overlap. But this is, of course, just a way of thinking of it, because this will never happen as separate response curves in reality. In reality, what we will do is we will add up all these individually triggered response curves. And that will then bring us to our estimate of stress-induced cortisol. That is, by adding up all those individually based cortisol peaks, we get this green prediction, or ESIC prediction, the green line, which is really smooth. And it is based upon all the individual black skin conductance peaks that we measure with our wearable. Right. So let's look a bit at the mathematical aspects of the model. First, to recap it, we take skin conductance at input. We determine the skin conductance peaks in order to determine the moments of stress. We then determine the skin conductance peak heights in order to determine the intensity of the stress. And then we compute the expected cortisol response for each skin conductance peak, and we add everything up. And in mathematical terms, and you have already long realized this amounts to a convolution of the skin conductance peaks with the cortisol response curve. So basically what we do is we take the skin conductance signal, we determine the peaks and their heights, and then we convolute that with the cortisol response curve. And such a convolution more or less resembles something like applying a 30-minute delay, because our convolution kernel has its peak 30 minutes later. And in addition to a low-pass filter, because our convolution kernel is more or less bell-shaped, right? So that is what it resembles, but our calculations were the nice convolutions that we did. What is also clear is that if we take a convolution kernel that lasts 100 minutes, that means that we need a history of data to estimate what's going on now. So if you would ask me to calculate based on skin conductance the cortisol prediction right now, I could do that, but I would need 100 minutes in advance of skin conductance data. That's a lot, especially for a laboratory setup, if you think of experiments. But in real life, that's doable if you consider that you would be wearing the device all day long. Another thing that you could think of is, could realize, is that now our model can predict into the future. Because if we measure a huge skin conductance peak right now, we know that in 30 minutes time, our cortisol level will peak, right? So we can look into the future, and that is something that is really nice for applications, especially if those applications are in the area of managing your stress levels. Okay, with that recap, I wanted to end the first phase of my presentation, which basically showed how we took cortisol as an inspiration to come up with an alternative measure for stress that can be used with wearables, with skin conductance measuring wearables. And the second part of the presentation then, of course, needs to be the verification of what we are proposing, right? Because you can propose anything, but it only makes sense if you have some evidence that it's correct. And then, of course, our research question is whether skin conductance-based estimations of stress-induced cortisol, whether our ESIC values indeed correlate with cortisol measurements that we can do in the body. That is our research question. And at that moment in time, cortisol shifts from being an inspiration to being our ground truth, right? Because in this case, we would want to check whether our predictions are correct against actual cortisol concentration variations. So this is the way that we set up our experimental verification. We did a 4-hour experiment. We needed this long time because of the history that we need in data, in which on the one hand, of course, we gained a lot of cortisol concentration measurements because they will be our ground truth. And we did so by measuring cortisol in saliva. This is done by so-called saliva swabs. You can see one. It's a cotton swab that you take into your mouth for roughly 1 minute. It soaks itself with saliva, and then it is kept safe and sent off to a lab where the concentration of cortisol in saliva is assessed. So that is the way that we measured our ground truth. And then we also measured skin conductance. And you see here that we did that with the DTI-5, which is a device that has been made by Philips. It's CE marked, although it's not on the market. It is CE marked. And if you're interested, it's open for licensing, and you could look at the Philips Democracy website to find more information about it. So that is a device, a wearable that could be used in real life, and that allows us to measure skin conductance throughout the day. And in this case, we measured it throughout the experiment, which consisted of a variation of tasks. We included some tasks that were really boring, and we included some tasks that were really stressful. One was a psychomotor vigilance task. That is a task in which a participant is placed in front of a computer screen, which is dully gray, and every few seconds a tiny, slightly grayer pixel lights up. And the task of this participant is to press a button immediately afterwards. It's a boring task, and it's difficult to stay awake. That's why it's called a vigilance task. And participants did this for somewhat longer than an hour. Then we also included an NBAC task. That is a task in which you are given a stream of letters, and your job is to report whether the current letter is the same as the one and places back. Now, a one-back task is easy, right? That is just reporting whether the current letter is the same as the previous one. That's easy. But we did a 2-back and a 3-back task. So then you had to report whether the current letter is the same as the one before the previous one or the one before that. And those tasks, I can assure you, are relatively difficult. And usually you measure how well you perform on that by looking at the amount of correct responses, or by looking at the time that you need to give a response at all. So this is a measure of what we would call cognitive functioning or cognitive workload. And then the last task that we did was the TRIA social stress test. It is a test that is really known widely in literature and considered the utmost stressing task, because it asks you to do some public speaking. It tells you that in 5 minutes time, you will be asked to give a 5-minute presentation in a job interview. And before you have to do that, there are 5 minutes in which you are given some material about the so-called company that you are applying at to prepare your interview. And of course, this is fake. Every participant knows that there is no real job interview, but nevertheless, it is known to stress out, on average, participants quite a lot. So it's a test that is used very often in literature. So if you look at the procedure that we did it in a controlled lab session. And we started with the vigilance task in a dark room for 60 minutes, and we took some saliva samples. Then we had a pause. Then we did the ANBEC task, the cognitive task, took some saliva samples. We also asked participants to score how they felt using the PANAS questionnaire. And we took a saliva sample. Then we did the TRIA social stress test, the public speaking test. And immediately afterwards, we again asked them how they felt. And we again asked them to do the cognitive task. And that was more or less the end of the experiment, when we still then had an exit interview and debriefing, and we took some last saliva samples. Which brings me to the results. And of course, first we look at the saliva cortisol concentrations. So what you see here is on the vertical axis, the cortisol concentration in nanomoles per liter. And on the horizontal axis, we see the 9 sampling moments that we had during our experiment. And if you look at what happens over time, you see that at first there is a decrease, and it's even a significant decrease in saliva cortisol concentration. And we think that that is due to this psychomotor vigilance task that is really boring and not stressing at all. And what you see is that the cortisol starts dropping. It even starts dropping relatively after the psychomotor vigilance task, but that makes sense because cortisol is slow. Then what you see here is that there is this huge increase in cortisol variation, and that has to do with the TRIA social stress test. This is exactly what we expected. This is why we included the test. Again, you see that the increase is not immediately. It takes 20 minutes before it reaches this peak, and that again is because cortisol is slow. So this is what we found on average over participants, and it is very much in the way we expected it, and it aligns with other findings in literature. But when we took a closer look at the data, we found that this curve is not the same for everyone. We found that there were 22 participants who indeed showed this huge increase after the TRIA social stress test, and we call them the high responder group. But we also saw that there were 6 participants who did not do that. We call them the low responder group. And among them, there was one lady who actually had a consultancy company in which she prepared people for job interviews. So she was laughing at this task, right? She enjoyed it very much. So in this next slide, we have splitted up the cortisol results according to these 2 groups. And you can see that, yes, for the high responder group, we get the curve that we are expecting with a high increase in cortisol after the TSST. And for the low responder group, we don't. And from now on, I will be presenting the results for these 2 groups separately. Well, we did not only do cortisol measurements, we also did the psychomotor vigilance task, and we followed their performance over time. And here you can see that during the 60 minutes of the task, the reaction time of these participants increased. And this is as expected. At the beginning, you're still rather vigilant, you're quick in your responses. It only takes you 340 milliseconds to respond. But towards the end of the task, you're slower. It takes you 380, 360 milliseconds to respond. So this increase is something that we expect. What we also see is that there is not a difference between the two groups. And that makes sense because the two groups are based on something that happens after this psychomotor vigilance task. They are based on the Trias social stress test. So why would that have impact now? This is different if we look at the results for the effect that people report, the negative effect and the positive effect, as you can see in this graph. On the left hand, you see what they said before they had to go through the Trias social stress test. And on the right hand, you see what they found after the Trias social stress test. And the positive effect on the blue graphs doesn't show any difference. Apparently, if they felt positive before, they felt equally positive after. But there was an effect of the Trias social stress test on the negative effect, because before the test, they didn't have that much negative effect. They didn't feel so negative. But after the Trias social stress test, the amount of negative effect had grown considerably, significantly. And that is what is expected because the Trias social stress test is not something that is very pleasant. So, of course, your negative effect grows. Right. So, another comparison between before and after the Trias social stress test is how well did they perform on our cognitive test, our MBEC task. And what you see here is that for both groups, both the high responders and the low responders, there is a decrease, which means that after the test, their mean reaction times were lower than before the Trias social stress test. And that makes sense, of course, because these people were learning, right? So the MBEC task is a difficult task. You have to learn, but after a while, you get a hang of it and you get better and your reaction time drops. So the fact that it decreases is exactly what we expect. But something else happens as well. What happens as well is that the curve for the low cortisol responders decreases significantly more than the curve for the high cortisol responders, which basically means that the low cortisol responders were learning more than the high cortisol responders. Basically, it says that the Trias social test that has been in between here actually has impeded the learning of the group of people that reacted to the Trias social stress test. And similar results were found if you put not the reaction time, but the accuracy on the vertical axis. And so this is an indicator that the stress that is induced, the cortisol that is induced, in fact, affects the performance of your cognitive functioning. We knew that from literature, but we also see it in this particular test. Right. So let me now turn then to what is the main topic again of this presentation, and that is how we can use the skin conductance signals that we measure with the wearables and our ESIC measure of stress-induced cortisol to predict the actual cortisol values. So here again, what you see in the dark blue line is the skin conductance trace that we measured during the test. And what you can see on the bottom, the black peaks are the peaks that our algorithm derived from that, and that we sent into the convolution to get the ESIC estimate. And the ESIC estimate is here in the red line. And you can see that it varies smoothly, of course, because it has such a wide convolution kernel. What you can also see is the peak of the kernel is roughly 30 minutes later than the peak of the skin conductance responses. And that's also, of course, because we had this delay. So what you can see is that we have a sort of continuous prediction of what cortisol is, at least stress-induced cortisol is over time. And now we want to compare that to the values that we measured using the saliva cortisol swabs. But of course, those are only taken at certain moments in time. We don't have continuous information there. Those swabs were only taken at the moments of these green vertical lines. So the only way to compare our prediction to what we actually measured was by taking the average value around this moment of our red ESIC curve and comparing that to the value of the cortisol that was taken at the moment of this swab, and doing that for all 9 swabs of that were taken with the saliva. And if you do that, these are the results we get. And again, we split them up for low and high responders. So if we look at the high responders, you can see that the two curves actually very nicely overlap. What is on the horizontal axis are the moments of the samples that were taken, and on the vertical axis, there is the normalized cortisol, that is the orange curve as we measured it in saliva, and the normalized ESIC, our prediction, that is the blue curve that we normalized there. And you can see that the two curves are really nicely related. They actually have a correlation of 0.74, and that correlation is significant. For the low responder group, we see that the curves are different, but they are alike in this case as well. And also there, the correlation is relatively nice, 0.66, which is just not significant. So for both groups, actually, we find that our predictions, the blue lines, are substantially reflected in the orange lines. There are substantial correlations there. That's nice. It's not the only thing we want. What we would like to know is whether this holds for persons individually, because if we want to use such a measure in reality, it is not of interest that it works on an average group of people. Even if you split them up into high and low responders, it is important that it works for everyone individually. So what we did, and what I'll show you in this graph, is the data of one person only. He had 9 saliva swabs, and we also took the 9 ESIC predictions for those same moments in time. And this is the result. On the horizontal axis, we have the ESIC predictions. On the vertical axis, we have the measured cortisol information. And what you see is that there is a relatively nice correlation for this person of 0.76, right? It's significant in itself. It's the correlation for one person only. So this person, if he would walk around with this device and we would apply this measure, it would work for him. He has a very nice correlation. But as you see, not all correlations were this good. Actually, this is all the correlations that we were able to calculate for our 28 subjects. And I ordered them here up according to their value. So the highest ones are on the left and the lowest ones are on the right. And what we find is that the top 10 correlations, they were, of course, positive, but they were also significantly positive. And the one that I showed you just there is, I think it's this one here. It's not even the best correlation. There are even better ones, but it is in the group of the very good correlations. There were also 12 correlations that were significant, so they point in the right direction, but we didn't have enough information yet to make them significant. And there were also a few correlations that didn't go well. They were in the wrong direction. They were negative correlations. And luckily for us, they were not significant. So they are not predicting anything, actually. So one of the things that you see is that it's not the case that the high responders end up on one case and the low responders end up on the other side of the graph. Actually, the low responders are nicely distributed among the other persons. So it doesn't depend on whether you're a high responder or not. But apparently it works for many people, but not clearly for all. What we, of course, did was to see whether it would work individually on average. And for that reason, we calculated the average correlation coefficient. And if you do that, the best way to do it is to take a Fisher correction. We did that. And then we arrive at a Fisher-corrected correlation of 0.48, which is a very nice value, actually, in psychophysiological literature. And indeed, it tested to be significantly better, different from 0. So we know that there actually is an individual correlation there for most of the participants. So we were very happy with this result. And it brings us to the discussion. And if you look at what we did, then we modeled the relation between skin conductance from wearables and in-body cortisol changes. And we showed initial proof on the laboratory conditions. And I phrased it this way because that also points out to a number of limitations that are related to it. One of them, obviously, is that this is a first test only, right? So that means that this is nice, but more proof would be nice. especially that this test is only done in laboratory conditions. And we would like to see, of course, to what extent it also holds under daily life conditions. And a third remark that I need to make is that our ESIC skin stress-induced cortisol estimate is measured in arbitrary units only. Only the relative cortisol changes are assessed. That's for a number of reasons, because one of them is that stress induces cortisol changes in the body, but there are also other reasons for cortisol changes in the body, and those are not included in our measure. Also, we didn't want to actually calibrate that to some way, and that is why we took correlation measures in order to assess whether we found a relation. Of course, the limitations imply lines for future research, go to real-life circumstances, also try to get a detailed understanding of what this exact link between physiological processes, the hormonal ones of the cortisol, and the neurological ones of the skin conductance, how they are interlinked. And we have also an interest to look at the applicability and personalizability for individual use of this stress indicator in wearables. Which brings me to my last slide, my take-home messages. What I try to convince you of is that stress affects both our cortisol and our skin conductance levels. That since skin conductance reacts more quickly, it's possible to predict the stress-induced cortisol changes from our skin conductance ahead of time. And that idea is supported by initial experimental results that show a significant correlation of ESIC with saliva cortisol. And that is important because we have seen both in our experiment and in literature that increased levels of cortisol are associated with reduced cognitive functioning. And that makes that that ESIC prediction relevant for mental balance coaching applications. You could think, for instance, of an application that would monitor whether you would be in a cognitive zone that is still allowing you to function correctly. And it could then give you feedback that you would be nearing maybe the transition to a cognitive zone that is not that favorable anymore. And it could do that ahead of time. So that would make a device that would allow you to actually manage your stress levels and not only observe them as they happen. So basically what we did was we took cortisol, we took it first as a inspiration and then as a ground truth for the development of a stress indicator, and then it pays off because now we get less variability due to self-reports, and we have a measure that reflects cortisol, which has direct implications for cognitive function. And that is the presentation that I wanted to give to you today. Thank you for your attention.
Thank you very much, Joyce, for your presentation. We have some questions from the audience. I will go through them now. The first question is from Felipe, who asks, is the skin conductance measure affected in the case of people who sweat more than other people? And if so, how do you deal with that?
Yes, yes, of course. This is the case because, yes, our sweat glands react to our autonomic nervous system, and the reason that they fill up with sweat in the case of stress is an ecological one, because you might know that when your hands are a bit moist, they have more friction. And this is something that is important for you if you need to run away. If you have more friction on the soles of your feet and on the soles of your hands, back time in history, that will allow you increase your chances of survival. So this is the reason, the ecological reason why we think that if we are stressed, our autonomous nervous system, our sympathetic branch triggers the water content in our sweat glands. But of course, it's not the only thing that triggers this water content. And Philippe is right in saying that, yes, also if you're sweating because you are being active, you're exercising, this is something that will trigger your skin conductance. And this is the case. And so what you often see is that the skin conductance level increases because there is just more sweat in your sweat glands. The conductivity of your skin increases because water is a good conductor. So this is another source of information. And Philip is right in the fact that this is a confounding source of information. So what we've been doing at Philips is trying to mitigate that as much as possible. And one of the things that we found out was that, yes, if the skin conductance level increases because there is more water in your content, we can still be looking at the peaks, right? Because in our algorithm, we're looking at the peaks, and the peaks remain there, whether the base level is low because you're not exercising or high because you're exercising. Right? So our algorithm inherently has some sort of mitigation against the fact that indeed for physical activity, your average skin conductance level increases.
Thank you. We have 1 minute and a half left.
Okay.
So I will go rapidly. Did you observe alignment between the cortisol levels and the PANAS self-reports?
We didn't look at that. We really didn't look at that. I think that if we would have to do that, we would see, we would have to take the PANAS self-reports just before and after the test. And then we would take the cortisol levels just 30 minutes before the test and 30 minutes just after the test because of the delay. We could do that. Our research is really different from the research that is usually done in the research of cortisol in the respect that they usually take the peak cortisol level, or they just take only one level 30 minutes later. Whereas for us, it's important to follow the dynamics of the cortisol. We've been looking in literature to see what is known about the dynamic of cortisol, and it's not much actually. So we haven't made that regression back to the normal procedure that is indeed in case of standard stress and cortisol research, that you take only one cortisol value and correlate with that.
We have 10 seconds left. You are welcome to answer the questions directly on chat. And as for the attendees, in 10 minutes, we will start with the mining for program comprehension session.